Hello everyone. Welcome back to our vector journey. Now imagine this. You're playing a video game where your character moves in a particular direction. You press the run button and suddenly your character moves twice as fast, same direction, double speed. That's exactly what multiplying a vector by a scalar does. It scales your movement. So, let's dive in. We start with a vector A and a scalar. Let's call it lambda. When we multiply the two, we get a new vector lambda A. That's lambda times A. This operation is called multiplication of a vector by a scalar. Now listen carefully. The new vector lambda always points in the same or opposite direction as A. If lambda is positive, direction is same. If lambda is negative, direction is reversed, like driving forward or throwing your car in reverse. And the size, or the magnitude, is stretched or squeezed by mod lambda times mod A. When lambda equals 0, poof, the vector disappears. We get the 0 vector. And that's the basic idea. Scalar multiplication stretches or shrinks a vector, never tilts it. Pretty neat, right? Okay, let's take this idea a step further. What happens when lambda equals -1? Well, that's the mirror image vector. The same size but exactly opposite direction. In symbols, we write a plus bracket minus a bracket equals 0. Yup, just like moving forward 5 steps and then walking back 5, you end up where you started. Now let's talk about the superstar of vector normalization, the unit vector. If you take any non-zero vector A and divide it by its own magnitude, you get hat equals 1 upon mod A into A. That's your unit vector. Magnitude 1, direction unchanged. Think of it like saying, I don't care how fast you're going, just tell me your direction. Unit vectors do exactly that. They preserve direction and ditch the magnitude. Alright, now let's put on our algebra hats. Suppose A equals A1 I hat plus A2 j hat plus A3 k hat. Now multiply by a scalar lambda. Each component gets multiplied individually. So, lambda equals bracket lambda A1 bracket I hat plus bracket lambda A2 bracket j hat plus bracket lambda A3 bracket k hat. Notice something? The direction doesn't change, only the size of each component does. It's like turning up the volume equally on all speakers. Sound pattern same, just louder. Now, two vectors are said to be collinear if one is just a scalar multiple of the other. That means B equals lambda A. Or equivalently, B1 by A1 equals B2 by A2 equals B3 by A3 equals lambda. That's your collinearity condition, a perfect linear relationship. If all those ratios match, the two vectors point along the same line. Now, mathematicians love order, and vectors follow some beautiful rules when combined with scalars. Let's recall them. 3 golden laws that make vectors behave like good citizens in algebra land. 1. K into bracket A plus B bracket equals Ka plus Kb, that's distributive law. Multiply first or distribute later, same result. 2. Bracket K plus M bracket A equals Ka plus Ma, that's scalar distributive law. Kind of like splitting a pizza into 2 parts before sharing. And 3. K into bracket Ma bracket equals bracket Km bracket A, that's the associative law. No matter which scalar you multiply first, the product remains same. These laws make vectors part of what we call a vector space. A fancy way of saying, everything stays nice and predictable when we scale or add vectors. Alright, let's get our hands dirty with an example. We are given a vector equals I hat minus to j hat. We need a vector in the same direction as A, but with magnitude 7 units. Step 1. Find the magnitude of A, that's mod A equals square root of bracket 1 square plus bracket -2 square bracket equals square root 5. Step 2. Find the unit vector. That's A hat equals 1 upon square root 5 into bracket I hat minus to j hat bracket. Step 3. Multiply that unit vector by 7 to get the required vector. So 7 hat equals 7 upon square root 5 into bracket I hat minus to j hat bracket. Now, let's check the magnitude just to be sure. Mod V equals square root of bracket 7 upon square root 5 whole square into bracket 1 plus 4 bracket equals 7. Perfect. Verified. And just like that, we found our vector, same direction, new magnitude. So if you ever want to change the speed of your vector while keeping direction, just scale it by number. Easy peasy. Time for a quick wrap up. Today we learned that multiplying a vector by scalar stretches or shrinks it, like zooming in or out on a photo. But the line of action stays the same. Positive scalars keep direction. Negative ones flip it. In component form, each coordinate scales by the same factor. And remember, a hat equals 1 upon mod a into a gives us the direction-only version of any vector. Two vectors are collinear if their component ratios match. b1 by a1 equals b2 by a2 equals b3 by a3 equals lambda. And the distributive and associative laws make sure everything stays consistent in our vector universe. So that's the power of scalar multiplication, a simple concept that controls magnitude without messing with direction. In the next video, we'll explore how vectors interact with each other through the dot and cross product, where direction finally joins the party.